going to talk about the joint curve interval now. Part of this work is work in progress. That is part of it that we know do that maybe say something about that you know to do. So a little bit of background. I'm going to talk about molecular homology. Something like a special Hegel diagram. When the generators are very easy to understand, and so these will be some somewhat combinatorial generators called Kaufman state. And also discuss some algebra related to the problem of computing molecular homology, something like computing. And along the way, there will be some algebra that will help us do that. So this is the plan. So first of all, we are going to study knots in a string, or equivalently, you can think about knots in R3. This will be piecewise linear or Sun's knots, and then we have a few special examples. Some of these we will revisit later on, but the all knot clearly, and the left-handed trefoil is, I guess, the next non-trivial example. The right-handed version is also familiar example, and I also included some more complicated examples as well, so that we won't always see the easiest example. Okay, so maybe back to these examples later. Knot-Floer homology is some kind of invariant for knots. This Knot-Floer homology was defined by J. Rasmussen, and definitely by Victor. So you had some lectures, I believe, by Robert Lifshitz when he talked or discussed the Knot-Floer homology. I will also give you some background on it. But maybe the easiest way to think about Knot-Floer homology is that we have such a knot, and we have some extra data, so we start with a knot. And somehow we present it through a two-pointed Hegel diagram. So there is going to be this topological way of representing our knot. So there is going to be some additional data, which is a Hegel diagram. This will be a Hegel diagram of S3, so the underlying stream manifold will be relatively simple, but there will be two additional points on it, and it turns out that's enough to recover some kind of knot with the underlying stream manifold. So there is this topological data, and in fact, even that topological data gives you some generators. So these generators will have two kinds of grading, which we call I and J, but traditionally this is called the Alexander grading. And this other thing is called the Maslow grading. And our generators are going to give us some freely generated abelian groups, which are labeled by two numbers. So it is I and J. So a typical one of these finitely generated free abelian groups will be denoted as Cij. But if we are willing to do some more work and so this is the topological information here. And that part is actually not that hard, but we also have some analytical input. such as complex structures on the Hilbert surface or perturbations, then there is also a boundary map, and this is going to be a map connecting C and J ions. Okay? So if C of K is the sum, then there is a map from here to there. Its square is trivial, so B square is 0, and then we can take homology, and at the end out of this we get a homology theory. So the end product of this whole process is some kind of homology groups labeled by two numbers, A, I, and J, and of course they correspond to the number K. So in a very brief sense, this is how one defines non-Floer homology. Do you actually remember the definition of non-Floer homology by two-pointed Hilbert diagrams, or should I review that from Robert's lecture? Maybe very briefly. So an example is the best way to go. So here a very simple Hilbert diagram of SC. So its genus is 1. We have an alpha circle and a beta circle. And so that gives you a Hilbert diagram of S3. And I said in the Hilbert diagram with two additional points, I could choose maybe these 2 points. So as soon as you have that picture, which in general would be something like collection of circles, alpha 1 to alpha G. This is a genus G surface, and 2 points on it, but also a similar collection of beta circles, and I'm not going to do that. So a usual Hilbert diagram has lots of alpha circles, one kind, and lots of other kinds. Maybe I can do a few. Again, a very simple example. But so if you have that, then you can do the following trick of forget about the other set of circles and just concentrate on the first kind. Now this picture gives you a standard handle body. So this picture gives you just a solid handle body. Something that can also look like this. But inside that solid handle body, you also have these 2 points, and you can connect these 2 points by an arc, so that this arc avoids all the other alpha circles. So now this is just a small arc, but you can also push it to inside that handle body, and then you have a small unbounded arc. It seems like this is always trivial, just a small arc in one handle body. However, there is also, when you realize that there is actually a C-manifold here, there is this other set of circles, and you can do the same kind of process on the other side. Again, look at these beta circles, the blue ones, and again connect these 2 points by an arc that avoids these other sets of circles, and then you get another very tiny arc, and that you join these 2 tiny arcs, then you get an invalid circle. So in this example, it's actually very simple to see that you get the unknown. In this example, you can also connect these 2 points in the complement of the alpha, small arc, push it to one side, the other side, easily you see you get the unknown. So this is a silly example, it gives you the unknown. And you can see that there is one intersection point between alphas and betas. And then you can also see that for the unknown, this whole homology theory is going to be very simple. It's this group that we talk about is C, is generated by one element, and there is no boundary left because there is no room for a boundary element. So the homology for the unknown is C, and it's supported in binding 0, 0. However, as it turns out, one can do slightly more interesting things. And maybe let me give you another example. So this example is also on a genus 1 surface. I take this rectangular region and glue the ends of the two sides together and this side there. So this is a torus. Inside there are two kinds of circles. Maybe I draw it. This will be maybe alpha, and the other one is the other one. So if you look at this picture, again you get a Hegel diagram, and you can easily convince yourself that up to isotope, if you forget about the base point, then you would get a very similar picture to this one, to an isotopic picture to that one. You can get rid of some of these extra intersection points. And so this is again a Hegel diagram of S3. However, when you use these two base points, then it's a slightly different picture, and then you can ask yourself, what is the knot that is represented by this picture? We know what the strategy 2 should be. We look at a way to connect these 2 points in the complement of the alpha circles, and then push it on one side, and we also connect them in the complement of the beta circles, and then push it to the other side. And you can see that it's going to be slightly more complicated than before. And if you have never seen this example, possible. I would like to pose as an exercise to see that the corresponding knot is in fact the same as our second example is the left-hand example. Again, this is an example that is very, very simple. If you remember how Hegel phenomenology works from the lectures of Robert, you usually take G alpha circles and G beta circles, and then you intersect them in all kinds of ways. But here you have just one of each. So that means that we only have 3 intersection points. So our chain complexes has such 3 generators. One can actually find these bigradings, a little bit more work to define these bigradings I and J. But then you can realize that A will give you a generator like this, B will generate that, C, and C will generate the third one. And again, there is no room for a boundary map. So in this example, you can conclude that the homology of the left-handed platform is given by that picture. I should have said that that in this story, of course, the first input is the knot. You want to compute an invariant of the knot. The second thing is that there is this funny way of representing the knot by a two-pointed Hegel diagram. There will be lots of different ways of representing the same knot with different diagrams. And these different diagrams could easily give you different number of intersection points. Even in this example, I could move these things around a little bit and somehow introduce extra intersection points to have 5 intersection points instead of 3. And so the number of generators is not an invariant. TheseCij's are not an invariant. What you really can prove is that the homology you get after you divide the boundary map is an invariant. So the non-square homology is really the invariant of the homology of this picture. That's the only thing that's well defined. Okay. So eventually I would like to say something about how to compute in general, which will get actually not so easy but I thought maybe before we jump into how to compute something very complicated, maybe let's start with what's known about the firm. After all, when somebody comes up and tells you that there is this invariant, then you can always ask, well, okay, so is it good for anything? And that's a very reasonable question. So a few things that we do know about non-zero homology. So one thing is, which is actually easy to compute, is the other characteristic. So you can take the sum over I and j of something like -1 j times the ren of j multiplied to t to the I. And that is a well-known invariant. That's called Alexander polynomial. Fairly simple invariant. There's lots of different ways to compute it. For example, you can use scale relations. You can understand what happens when you locally change the crossing from a positive crossing to a negative crossing or resolve it. And then the statement is that the Alexander polynomial of the positive knot minus the Alexander polynomial of the negative knot is not a link, so these are oriented knots of links, always equal to p1 minus p minus 1 times the Alexander polynomial of this results. So in general, the Alexander polynomial for a link is a polynomial in p1 p minus 1 For a knot, it's an actual polynomial in p, and it satisfies the scale relation. And if you add the normalization that the Alexander polynomial of the knot is equal to 1, then there's a unique knot or link invariant that satisfies this problem. So this would be the same as going back to the definition and realizing that if you fix I, then there are all these chain roots for that I. And the alternating sum, if you fix I, then you get these alternating sums of the ranks. So this that statement is the same as taking the Euler characteristic of each of these lines, calling them AI, and then taking something like this Euler characteristic times p to the I is equal to the Alexander polynomial. You see what I did confused? We only do J I. I don't do the last one. That's the only thing that is so far. Okay, so again, bit of an anticlimax. The Alexander polynomial is very easy. You don't want to compute it this way. But at least it tells you that that is related to some classical invariant. Now, so that's one thing. Unfortunately, the Alexander polynomial is sometimes very simple. For the unknown, it's 1. And there are also other knots that for which the Alexander polynomial is equal to 1. So at least in the few of them here. This is one of the pretzel knots. There's an infinite family of pretzel knots. So here it's an example that Alexander polynomial is 1. HUN-REN knot, famous example, Alexander polynomial is 1. Kinoshita is also equal to 1. By the way, know that these two knots are almost the same. They are related to some operation which is called mutation. And that mutation is something called a HUN-REN mutation, which is that in the diagram you find a circle that intersects the knot exactly 4 times. You take the inside of that circle and just flip it over, there's the C2 action if you like, and then glue that back in. And so these are HUN-REN mutants. So the first thing one would do, and this was done a long time ago, is to ask where is that not the homology any better than the Alexander polynomial, and then you can, for example, compute not the homology or some special values of it for all of these examples. And then we realize that sort of explicit computations that in this case, so these examples, A times A is not the same as in fact, you can prove more, so that's just sort of explicit calculations in some special cases. There is also a theorem. If A is not the unknown, statement is that that for a non-trivial knot, this full third homology, not third homology, will be larger than for the unknown. One can actually say a little bit more. So one observation first, that in any diagram you have finely many intersection points. So because of that, some of this chain complex is finely supported, so the homology will also be finely supported. So even if the knot is very complicated, you will have only a few non-trivial third homology groups. But then you can take the region when the third homology is non-trivial, and in fact you can take a number T, with the property that the sum of H up H, J is non-zero, and on the other hand, H, I, J, K is 0 for I greater than T. So this would be going from the right, the first non-trivial line on which there is some interesting homology. And the statement is that if you define T that way, then T is equal to the genus, the cipher genus of homogeneous Seifert surface that bounds the knot. The special thing about the unknot is that the unique knot for which the Seifert genus is 0. And so you can immediately see that this theorem implies that theorem. But you can also see that you can recover the genus. Okay. So there's a few things, a lot more that also known about non-fluid homology. Maybe I'm not going to state all of them. One small remark is that there is this mutation, and the mutation does change the non-fluid homology, and one reason for that you can compute it, and the other reason is that you can also compute the genus, and the genus of them are different. This is Seifert genus 3 and this is Seifert genus 2. But what's sort of interesting is that when you actually do make a complete computation of these non-fluid homologies, and you take the sum of the rank for the Kirschner terracotta, then you get 33, and then you make the same summation for the Calvin knot. You also get 33, and so maybe it would be more interesting to say what we don't know about non-fluid homology, a few things that we don't know. So there is a conjecture, or I hope, but I first heard it from Adam Levine and John Bonnet, which is that Conway mutation don't change the total rank. So this is one thing that we don't know. And there is another conjecture I wanted to mention. And that's a conjecture of J. Rasmussen, which asks about the relationship between two different kinds of homology theories for knots. One is non-fluid homology, and another one is quantum homology. So the conjecture is that there is a spectral sequence over CO2 starting from reduced form of a certain Is that still a valid?
It's a valid question. I don't know what I actually conjecture.
Okay, so conjecture question. So your observation was that there is an inequality between the ranks. You know, every example that you want. All right. Very good. So maybe without further ado, let's go to calculation. There are different ways available for us now to make calculations for non-fluid homology. So there are already some methods. There are some very painful methods that work for small knots, but there are also more conceptual methods. So if you see this the first time, I'd like to mention that there is a combinatorial definition. Using grids, and this is due to numbers. And situated circle. There is also more algebraic method due to plotting and beginning. What's sort of common in these examples of these computations is that we have a relatively difficult problem, which is to understand the boundary maps. But in some special cases where you are willing to consider a Hilbert diagram, when you have really a lot of generators, then some of these problems are simpler. So, just to say a few things, I'm not sure how easy to use Walden's method, but I spent some time in this combinatorial or grid presentation of node topologies. For small nodes it works beautifully, so if there is a computer program that's willing to make computations for node topology, and if you plug in the conway node or the conditional terracetter node, it's a few seconds it computes the answer. However, when you want to compute slightly larger nodes that have, instead of 11 or 12 crossing, maybe 13 or 14, then it basically dies most of the time. So there's a certain limit to how much that could compute. For small nodes, it's perfect. But it has this interesting feature that in order to make the boundary map simpler, you need a lot of generators. And it seems there's a trade-off in that. The least number of generators you want, and some of the more complicated is the calculation. So the calculation I'm going to talk about starts with the Hilbert diagram that we have seen a long time ago, but we didn't know how to compute the boundary maps using that Hilbert diagram in general. So here is a special Hilbert diagram. I hope at the end something else will come out of this. But, okay, so this is a Hilbert diagram that's very well suited for our purposes. It starts with a node projection, and we're going to get rid of these complicated examples, and I will demonstrate that with the left-handed trapdoor as our running example. So we start with a node projection like this in the plane, and in addition we also use a marked edge. So the input is that actually, to make matters a little bit more complicated, we also want to orient this picture. So this is going to be forever oriented now. So what we want is starting with a picture like that, we want to get a Hilbert surface. Sigma. And if we have n intersection points, n double points, then we want the Hilbert surface as a genus n plus 1. Inside, we want a collection of alpha and beta circles and two base points here. That recipe is actually very simple. So When we have a crossing like that, we replace that crossing to a punctured sphere. And of course, corresponding to an edge, you just have an end loose. So something like this, abstractly, will be replaced. So in our running example, let me just draw the resulting surface. And this is supposed to mean there is also this depth, or the third dimension also. And I hope it's really achieved. Alright, so that's the surface. That was very simple. Actually, that surface itself doesn't even remember that there is an over-crossing or under-crossing. So that's something. Some information that we still have to include. We have a marked edge somewhere, and for that we are going to have a very special circle that will be one of the. So this is for the marked edge. Other than that, for any crossing, we also need a circle, and that will be this circle. So in our picture, that will be something. Is that okay so far? So these were the four, or in general, n+1 meter circles. Then we also need the other set of circles. Perhaps do them. So there is a special mark point, and it has two sides, two special regions, and one of them we will just forget about, but the other one we will just every circle. So basically, should have said that when you have n crossings, then you have also n+2 regions inside the sphere for the domain. One will be special, maybe the one that contains infinity, but for every other contour, we'll have one of these alpha circles. So turns out that's a Higard diagram. You can convince yourself it's a Higard diagram as 3, but you have to see that each of these circles bound either in the inside or outside discs. The contour certainly bounds discs. The circles also bound some discs in the inside. So this is at least a Higard diagram. And 3, we also need the 2 base points, and somehow depending on the orientation. Here, we put the base point C here, and the other base point is down here. So I claim that, but first of all, you can always do this, right, for an arbitrary knot projection. And the claim is that this is a Higard diagram for the knot. And for that, what we have to see is that it's possible to connect the 2 base points. In the complement of the alpha circles, that would be easy. And in the complement of the beta circles, you can also do that, go around. I know my picture is not best possible. Okay. Maybe it's easier to look at this more general picture. So when you go around, you come from somewhere, and if you are coming from the top, that's fine. If you are coming from the bottom, you want to come up to the top, because then you can go through that circle. And when you are again trying to go through this region, your circle allows to do that on the back. And then you can see that the corresponding picture will be actually lower. So you will really get that. Any questions so far? Okay, so this is a Hegel diagram, and it's very simple to get the generators of non-flow homology of the non-flow complex. I don't want to go into really detail, but you can see that in a typical place you have your, around the crossing you have these circles, and the alpha circles, and you have as one other special circle, the beta circles, and they intersect. We have locally the choice of 4 intersection points. So if you want a coordinate on each of the beta circles, you have to choose one of these 4 things. And this one of these 4 things are really correspond to the corner. So basically, locally, you have this picture. And for that intersection point, you have to choose one of these corners. There are 4 special corners, and you have to choose one. But this is not an independent choice. If you really want to get a generator, then you need a collection of exactly G+1 points in the surface, so that every alpha and beta circle gets exactly one coordinate. So you have the condition that each crossing gives one power from corner, these are called power from corners. But you also have the property that every circle needs exactly one power from corner as well. And you can see that this special region can only pick up this intersection point, right? This circle needs an intersection point. So when you think about these Kaufman corners, you have n crossings, you have n+2 regions, but 2 of them will discard the 2 sides of the special body, and you end up with n other regions, in this case 1, 2, and 3, and you have to find all the Kaufman corners. Maybe just very quickly, let me do that in this example. So what are the Kaufman corners here? One possibility is choose A, A, A. In that way, all 3 crossings and all 3 of these regions get a corner. That's one possibility. I could choose to do this slightly differently. B, B, B. That would be another choice. And we can also have here something like C, C, C. These will be the 3 different choices. So far it is very simple, and you can get a local way of getting both of these numbers, the Alexander and the Mastov limits. So they just very quickly. Both one corners. Locally. These I and J terms. And the I, that corresponds to the Alexander gradient, is given by, locally I have these 4 corners, and this is -1/2, this is 1/2, 0, 0, and J again for the negative, for the other one. Here we get -1, 0, 0, 0. And for the other crossings, we have the opposite. Bottom line, you could calculation for the trefoil. Locally, you have three. So, for example, look at C. C has three different local Kaufman corners, right? Each of them picks up a certain term, minus 1/2, 1/2, you add them up, and the sum of them will give you the corresponding i's and j's. So, if you do this calculation in this example with the choices that we have, then you again get these. This should be corresponding to A, this corresponds to B, and this should correspond to C. So we have discovered this a long time ago that we can always do this and find at least a Hagar diagram that gives you a small enough number of generators, and you can compute these local contributions. Of course, the problem is that that's not enough. We want more than that. We also want to understand the boundary map. So this approach gives you a partial answer. So in special cases, case alternating, it actually works beautifully. Alternating means that when you go around the knot, the under and over things alternate. So you go under, over, again under, and so forth. So this will be alternating. And in case of an alternating knot, you can easily show that you look at all the Kaufman states and you compute these numbers, then all the Kaufman states will line a certain line. So this chain complex will be supported in a line, and because the boundary map goes downwards, there is no boundary map. So for alternating knots at least, you can do this calculation easily, and you don't have to compute the boundary maps at all. Of course, the next question is what happens when it's not alternating, and again the naive approach is that that's okay, so that means it's not always alternating, and locally at least you can find this pair of Kaufman states that differ only locally at these coordinates, and then you can find some small maps connecting these Kaufman states. So at least we can do some partial calculation, but it wasn't clear how to do the general calculation. And this is what I'm going to talk about. So how to do the calculation. So the input is the knot. There is a knot projection, and this is what you see. And there is a somewhere marked edge on it. In addition to just having an arbitrary projection on the plane, we are going to have a special direction. So a typical knot, you can always put in this position of starts with the maximums, and then we go around and there will be some crossings, maybe lots of crossings, and at the end we will have some minimums. And at the end, if you really want, you can put the last minimum to be the one in the marked edge. So this is going to be the input. This on the top we have maximums. Then exactly how many maximums we have is called the pitch number or the pitch bed. And then, well, the hard, just an interesting thing will happen in the middle. There will be some crossings, lots of them, and at the end, then we are going to finish that. So great. So the idea is instead of looking for some magical combinatorial way of saying when do two Kaufman states give us a map, we are going to build up a more complicated series. So in this case, we have this same knot oriented, so it might start like this. We have a number, namely how many strands goes through that line. And that's going to be even, so we have this even number 2n. We also will have, in general, a picture when half of these strands will go up and half of them go down, something like this, in the middle. So we are going to have an algebra there's going to be an algebra associated to a picture like that. And what we're really going to compute is what Robert Lipschitz called the D module. Okay, so very quickly. How do I want to think about this D module structure? Practically, you should think about this as some kind of scanner. It starts with the knot, it starts at the top, and that's a read of the knot. And at any given time, when we stop here, somewhere in the middle, we will be able to get some information about what happened up there. We don't know what's happening down here. So we will have some kind of Kaufman states for the top portion. These will be our generators. And then we also have a boundary map. But the boundary map is not the usual boundary map. So we work over Z12 coefficients. But we also have an algebra where we Z12 coefficients. So the way you want to think about them is that D of x, instead of x being one of your generators, instead of just being some sum of other generators, but a typical thing would be some a times y plus b times z, and so forth, and these are algebra elements. And this is going to be a DGA. There will be a differential in it. So some of these algebra elements we have non-trivial differentials as well. So a D module is something where D square is 0. But that D square will have terms also derivating y, but we also have terms that are just derivating x. I use the letters. Maybe to drive through this point, it all starts with one maximum, so you can understand what happens there. Is that the thing? So we have two of these strands, usually two ends of them, and then I need some generators, right? And I also need some algebra elements. So first of all, what is the algebra? The algebra will be generated by U1, U2, so these are some elements. A typical algebra element would be U1 to the n, U2 to the n. U1 times U2 is 0. But there will be also something extra about orientation. And so far we don't see any differentiation, but then we have an extra element, which in this case would be C1. C1 squared is 0. We'll use C1 because 1 is oriented up and 2 is oriented down. And D of C1 is U1. So in practice that means that our actual algebra elements are these, but we also have C1, C1, U1 to n, and C1, U2 to n. This is an algebra. It seems a little bit large because you have arbitrary powers, but other than that, it's not very complicated. So this is the algebra that D module is generated by one element x. The fact is that this region doesn't need a Kaufman state, so we don't care about that. But this region does. or we don't know, maybe it does, maybe it doesn't, but we assume that it perhaps does, and that will be our generator X, basically corresponding to that missing Kaufman state, and B of X will be C1 times U2. So this is an example. I just wanted to demonstrate that having a B module is not a very complicated object. It's almost like having a chain complex. So let's look at this. Great. Here, when I apply this twice, I get C1 squared. It's not to be C1 squared is 0. So that part is okay. I also will have the term, well, I should have said that D of UI. I also will have the term of U1 times U2, but that's also 0 because of this condition, right? So it actually does satisfy the property that I want. So this will be how it generally works. I got a module here, a D module, and what we need is 3 parts. I have, I guess 4. I have to tell you what is the algebra, first of all. I have to tell you what is the D module. Actually, that's very simple. And then there is the interesting bit, is that I have to understand from above there is some kind of D module coming, right? There is a certain D module. And now I want to introduce a crossing. And this is sort of the engine of the construction. That crossing will give us a transformational rule. There is a certain D module coming in, and there is a certain D module coming out, and that rule is this, what Robert called an AD module. Locally, it will be generated by all of these Kaufman states, but then we really have to understand that. So that is another part, and strangely enough, the hardest part is finishing off when comes, in this case, comes a D module over something, some larger algebra. But now, when we go through this closing off, then we simplify the algebra, but still somehow the way it is set up, this is sort of the hardest formula in the whole calculation. And at the end, then we also finish it off by these double points. Here we have 2 options. Either you want the non-flow homology, which is a simple object, that gives you a very simple A module, or you want the filtered version, which is slightly more complicated, but both of them you can get. So I have like 2 minutes. So the question, do you want to hear the algebra or why this works, or no? Okay. So in general we have these 2 and 1, 2 and stands. And we also have these regions A0, A1, A2, and let me talk about the part and we don't have the C's yet. Basically, that is a very simple example, n equal to 1, but some of the features are also going to appear in general. So basically, sometimes you have C's. These C's correspond to the parts that the stands go up. Every stand will give us some kind of U's. So we will have, in general, actually, a multiplication of an arbitrary polynomial Z U1, U2n. There will be a multiplication of that. Sometimes some terms will disappear. Like here, U1 times U2 was 0, and with similar cancellations in general. Okay, so what is the algebra? You have the way you want to think about the algebra is some kind of motions. So first I have to tell you motions between what? and what motions are allowed. Motions within what will be related to these Kaufman states, namely, some of these regions don't yet have Kaufman states, and I have to remember which one were not yet have a Kaufman state from above. So basically that means that I have here 2n minus 1 regions that possibly need Kaufman states, and I have to choose n of them. So this is how it works. So I have 2n minus 1 choose n choices. Each of these choices will call x, y, or so forth. So for example, this is one choice that we look at n equal to c. Then, for example, this would be one choice. So, this is a typical coordinate, choosing these n coordinates out of 2n minus 1. And I could also have another choice, y. And a typical algebra element will go between them, so we go from here to there. In the previous example, n equal to 1, then we had just one choice. It wasn't sort of obvious there. But here you have several. So a typical algebra element will start somewhere and end somewhere. And that means that I can only multiply non-trivial algebra elements where, so if I can multiply them in this case, when the end of A is the starting of B, then A times B makes sense, otherwise it doesn't, so then it would be 0. There are some special algebra elements going from x to x that are almost the same as 1s. So these are idempotents. So for each of these choices, 2n minus 1 choose n choices, we are idempotent. And that means that in this case, this is an idempotent square that is the same, and if I multiply with A, then I will get A back. And similarly, if I multiply A with I1, I also get A back. And I could take the sum of these idempotents, and that somehow is what I want to think about 1. But at any rate, a typical element like that, we have exactly n coordinates, right? I could just name these numbers. So that would be this x, shorthand would be something like 1, 2, and 4, right? So we have these coordinates, which are labeled from 1 to 2n minus 1. This could be x1, x2, and x3. And one condition is that if x, so if A is non-trivial, that implies that xi minus yi is less than or equal to 1. So that means that we have these n coordinates, and each coordinate can only move at most by 1. So now you can almost guess what the algebra elements will be, what will be sort of the generator of this algebra, exactly moving one of these coordinates by 1 and leaving the rest of them fixed. So R5 will be moving on the 5 strand to the right. So this will be R5. And L5 will be moving back. So we have these R1, R2, and in fact, it's sort of special because these coordinates are not allowed. So in fact, here is R2, and in a sense, these make sense in general, but sometimes x doesn't have a coordinate here or a coordinate there, then R5 doesn't make sense. So you can take one, you can think about this as one generator, but you can get several different generators out of them by multiplying these idempotents. So we have these, and we also have this algebra U1 to U2. So these are some of the algebra elements, and if some of them are pointing upwards, like this, then we'll have those as well. So this example will also have C2, C4, and C6. With the understanding that we see R. And this is almost the algebra. There are some relations with that and then these relations also have some consequences. So typically, right, in a typical coordinate, I could use Ri and then I could go backwards, right? And in that case, Ui is equal to Ri times Li. In that idempotent, in that if X really has one of these coordinates. So we have a few possibilities. Ui doesn't change in itself the position of our coordinates. It's just going around. So locally we have these four possibilities. This is the ice coordinate, and X may be occupied here, occupied there, occupied here, occupied there, occupied on both sides, or not occupied on either of these sides. And in this example, we want Ui to be 0. Otherwise, here it will be non-zero. We can multiply with Ui. In this case, again, Ui is not trivial, but we can decompose it. So in this case, Ui would be the same as R. So Li times Ri, back and forth, right? And here is the opposite. And we want Ci squares to be 0. And we want Ui's to commute to everything. And Ci's to commute to everything. As it turns out, that kind of commutation and that rule that sometimes used trivial will have consequences in the algebra. And so the nice thing to see is Ui's commute in everything. Okay, so for example, if X has a bunch of coordinates fixed next to each other, but then there are some coordinates that are missing, then the product of these Ui's that follows from commutativity and sometimes will be 0. So this is the algebra. And maybe just very quickly I can tell you what is a starting algebra and Imojo. So for a picture like that, again we have one generator X. Its outgoing idempotent is this idempotent for this choosing these regions. So one generator and the D of X is something like C1 times U2 plus C3 times U4 plus U5 times C6 times X. But to be more honest, what that really means is that D of X is I of 1, 3, 5 times X. So the bottom line is that we have one generator, but in that idempotent, U1 times U2 is 0, and UC times U4 is also 0, and so forth. So So this actually does make sense, this square is 0, and then you have to discuss the other part, which I really don't have time. And I'm sorry for your time.
Are there questions?
Why does this work?
Okay, so excellent question. So a very naive approach would be, and something that we tried a long time ago without border came along, is to, I mean, you want to compute some contribution of certain homotopy classes, right? It's completely okay to somewhere in the middle of the diagram just degenerate the whole inert surface and see what you get. Now, in easy cases you can see what you get, but eventually what's happening is some kind of fiber product. This degeneration works. There's a certain moduli space. It itself is one-dimensional, but it goes through the net when it degenerates in arbitrary fashion, maybe with really large multiplicities. These R and L and U are also going to give us the same kind of multiplicities. And what's happening is that in that sort of naive approach, you look at the fiber product, you want to understand what's the contribution of zero-dimensional moduli space, but in the net, even though originally it was zero-dimensional, the picture is more like there is some large, maybe 100-dimensional, depends on the homotopy class, could be just one, but could be 100. Two subspaces that are complementary dimensional, we want to understand its intersection. And it's just a mess. Now, the bordered idea is, instead of doing that, just use very special degenerations and sort of also perturb the diagonal. And what that does, it sort of forces the interesting intersections to be zero-dimensional on one side and 100-dimensional on the other side. But what's the nice thing is that from this side, you can always count zero-dimensional things. So when you think about the D module, it's really the contribution. You have these Kaufman states, and you want to understand homotopy classes between them. And you are really looking at, in a sense, zero-dimensional, it's one-dimensional of the direction homotopy classes. So it's no wonder you can do the part from the top. That the trick is, and of course this is the part that we didn't have any time to discuss, is what on earth are you going to do around the intersections? But of course one part of the trick is to really set up the holomorphic geometry so that you can sufficiently perturb the diagonal. And then you have to understand what is the algebra, the elements that you get. So our algebra is sort of a deliberately simplified version of the bordered algebra. We divided in some elements. Short answer, we use the bordered approach. Long answer, it's actually slightly more complicated. There were some problems with boundary degenerations. And in particular, the kind of orientation of the arcs is not because you need to orient the arc to get the well-defined value. That kind of orientation is something crucial in the analysis. So it was slightly more complicated in that sense than the border approach. So that, apart from that, it's just the same usual kind of thing. Then you have a certain moduli space, and then what you have to work out is the contribution of a crossing. You can work out the contribution of crossing locally. That ends up with working with some kind of pictures like that in the first symmetric product. So you have the alpha circles incoming and outgoing crossings And then you have to understand the holomorphic geometry of that picture. But then you have to understand high-dimensional volume spaces as well. So working out these 8D module those extra